Böyle çek. Tamam. Hatta şu televizyona yakın bir yere oturursan şuraya. Direkt konuşurken bir konuşmayacağım. Bir de televizyon çekersin, tamam mı?
Bir de televizyon bir şey. O taraftan mı çek?
O tarafta otur da. Bakın olur.
Tamam.
Yazılar daha iyi gözüküyor.
So, ladies and gentlemen, good morning, everyone. So, maybe my voice is harsh, but so welcome again for our 13th European Conference on Renewable Energy Systems. This was, as I say every time in every event, this is a project outcome. Just 13 years ago, we made a European project, Erasmus project, and therefore, after this project, with our partners, also including Francesco, thank you, and all other partners from different countries, we decided to improve and also widen this event each year, and now it came to 13. So that's very good, and it will also and also Professor Francesco Cottone was in Mallorca. We made it in Mallorca, Spain, and this year we are here. And next year we will be in another European country, I think. Actually, our the system is a bit different than the other conference because we have the conference proceedings in your USB. We have already delivered it, and this conference proceedings is made from the abstracts and also short forms of papers. So, but after the conference, in a few weeks, with the program committee members, we will determine and we will also examine all the papers and we will deliver them to different journals because we have lots of different journals from material science to the energy and all other scope. I mean, scope is very wide. So the program committee members will decide which paper will go to which journal, and then we will call to the authors with a list, well-defined list, to submit their extended papers to this journal. And our conference works in that way. And each year we have made this professionally, and we have produced conference proceedings and also journal publications. And it works very well up to now. And of course, each journal has its own author guidelines, and you should put some new results on the topic which you have presented here, maybe some graphic. And we have already evaluated your paper, and then said that we can add some figures, some methodology, and some other extended results to improve or enrich your paper for the submission of the journal. So that's it. In that case, our conference is like a small school, I can say, because we are giving some hints to make qualified papers for the journal, because we have Web of Science journals also, this Q1, Q2, and we also have the official journal, Journal of Energy Systems, my journal. It is now this year, Francesco, it will be listed as a Q3 journal in Scopus. It's developing. And that's very good for all of us. And in near future, I hope that it will be also listed in Web of Science. Maybe in 1 year, because 6 months ago, we have written a letter to the Web of Science and checked our journal to the inclusion of the website, and they replied us. There are some revisions should be done, and in the outdoor guidelines, and we did it, and let's say in 5 months' time, we expect a positive outcome from this discussion and from the collaborative websites. So that in that case it will be very good for our community to have this strong journal. It's a very good thing. And yeah, and today I am here because before we also came here many times for political projects, so therefore this classroom and this university is nothing for me. So therefore I would like to thank you also, Francesco, for his assistance and also help, and thank you very much for this. And I would like to, maybe we can say some words to the audience.
Thank you very much, Lola. So we are not too many. We hope that other people will come soon. But I'm very happy to host this year this conference organized by Harold. Also, it's a very nice, interesting conference, and in the theme of renewable energy systems. And we also work with our group. We work on energy harvesting since many years. And we had a very nice project together in the Erasmus project in this field in the past. So I'm very happy to host this event this year, and you will have also a chance to visit this beautiful city, which is not very well known. It's a little bit lost in the middle of Italy, but it's a beautiful city. And we will also have a very gala dinner then later on, and a light lunch here in this kiosk. So I hope that you will enjoy this event, and that it will be an opportunity to share together our knowledge and to meet together and make friendship also. Okay, so thank you, Ella, and yeah, we can announce our keynote speakers. First of all, I want to welcome Elena. Okay, so Elena, my phone. Okay, so and I will just introduce Elena. So Elena, she's a full professor of chemical plants in the University of Milan, and she's a very proactive researcher also, and she was for her contributions in the field of catalysts, catalytic process, and hydrogen production also. And so I'm very happy to welcome her here and to listen also to her talk. Okay, thank you.
Thank you for the nice introduction. It is a pleasure to be here in this wonderful city, and I thank the organizers, of course, for inviting me. And in these sunny days, I would like to drive you into a journey into solar fuels in order to understand which is the state of the art of let's say the main technologies that can bring to the development of fuels deriving from solar energy. Solar energy is the most abundant source of energy in our planet. We could get a widely highest amount of energy than what is consumed worldwide, but it is currently not possible to exploit it efficiently through modern technologies. In spite of this, blood-driven processes are very intriguing because they can use direct activation of reactions more possibly activated catalysts or materials under milder conditions than traditional conventional routes. In many cases, even at ambient conditions. Photocatalysis and artificial photosynthesis are among the most investigated topics nowadays. If you just pick up these keywords, solar fuels, you achieve in Scopus thousands of references, which are steadily increasing in the last 20 years. So it is a topic which is growing more and more. Solar fuels are intended as a method to achieve the storage of renewable energy in order to solve some of the main issues which are related with the storage and transportation of energy, or possibly also of hydrogen, because hydrogen itself can be used as a solar fuel. I will just pick up some examples of some high and low TRL, high and low technology readiness level technologies. For instance, Siemens is very active in the development of different solar-driven processes, and they are currently active on pilot scale and demonstrative plants. For instance, they developed a demonstrative process for the production of natural gas, synthetic natural gas, starting from green hydrogen, so hydrogen produced through electrolysis driven by renewables, in particular from solar panels, and CO2 captured from point sources. And a quite high efficiency was reported for these preliminary investigations. Synthetic natural gas is considered as a more promising way to store hydrogen, and so solar energy, because it has an existing infrastructure, so we don't have to modify something in the user's side, but it also has a higher energy density on a volume basis with respect to hydrogen. So it is a possibly smart solution to energy storage and distribution issues. Also, there is a strong driver, especially in Europe, towards electrification, but electrification cannot do everything. In particular, it is almost impossible to cope with some hard-to-abate sectors using just electricity. So, the other option, the other hints of research are towards different ways to exploit solar energy, not through electrification by solar panels, but a direct exploitation of solar energy. We can imagine different ways to produce synthetic chemical fuels by exploiting solar energy. One is the direct photochemical or photovoltaic process that tries to activate directly reactions in a homogeneous phase. In this case, we are speaking about photochemical activation, or mediated through a catalyst, so photocatalysis, activate these reactions by using photons. Photons harvested possibly directly from solar energy. Other routes try to exploit what is called artificial photosynthesis, something that mimics current photosynthetic processes through a sort of artificial or inorganic semiconductor that plays the same as the photosynthetic systems, or even by coupling some biomimetic plus inorganic catalysts. In other cases, we can exploit the thermal energy stored from the sun. So we just try to derive the current thermochemical processes, which are very well established towards different fuels, but we heat up these reactors using solar light. In this case, some pilot projects are trying to adapt concentrators, solar concentrators, in order to achieve a high enthalpy medium, or in other cases, but we have a higher number of transitions, so it is in general less efficient. You can use photovoltaic power in order to drive electric ovens, and this is in some cases also pushed by European Commission that drives some horizon projects on the electrification of chemical industry, of industry in general. And finally, we have electrochemical reactions. In some cases, you use a very well-established electrochemical way to produce hydrogen through water splitting, and you use this green hydrogen as hydrogen medium. So you use all the synthetic routes that already use hydrogen to produce fuels, but the hydrogen in this case has lower impact and derives from solar energy. Or some new low TRL processes for the direct activation by electrochemistry of these reactions. So there are a lot of ways in which you can exploit solar energy in this field. So you can imagine something that we will call solar refinery, in which you need basically a source of CO2. CO2 in these processes is nowadays always brought from point sources. So abundant CO2 from chimneys of combustion, high CO2 emitters, to be captured, of course, with different technologies which are more or less mature, but has an economic penalty, because these are all very expensive technologies. In some cases, you need a water source, and of course, something that exploits more or less directly solar energy. And you can have different ways to activate just by using photons, by using heat, by using solar electricity, in order to obtain different products which can be mainly used as green fuels. The different technologies have different levels of readiness. There are a few high TRL applications. The highest, which is already commercial, is the production of electrolytic hydrogen. So we need a photovoltaic panel to drive an electrolyzer. Electrolyzers for hydrogen production are already commercial, so this is, let's say, a ready-to-use technology. Some examples with relatively high TRL are photosynthetic and biomimetic photoreactors. Here you see an example of solar harvesting through bioreactors, in which in particular we are cultivating microalgae, which can be seen as a solar storage, solar energy storage to produce biomass. This biomass can be used for various applications, in some cases to achieve chemicals by selective extraction of some interesting chemicals. There are some genetic approaches that try to select microorganisms that can more selectively drive photosynthesis towards some significant applications. In this case, of course, we are more at the research level. This biomass can be also used to derive the oil, and so through the transesterification we can obtain biodiesel, or just to be dried and burned as a renewable biomass. water-to-liquid plant. It has been built in Germany very recently. It is intended for the production of Fischer-Tropsch fuels. Fischer-Tropsch is a very, very well-established reaction that uses CO and hydrogen. Of course, hydrogen is intended as green hydrogen, and also CO is intended as green CO because it comes from the reduction of CO2 to CO. And so, when you have syngas, the mixture of hydrogen and CO, just by playing with a very, very basic industrial chemistry, you can do almost everything. You can produce methanol, light fuels, synthetic fuels through the Fischer-Tropsch. You can open all the conventional refinery processes. And another interesting application is the Synhelium's dome plant. It is also very recent, 2024. That is driven by thermoactivation. So you have this field of heliostats and also some photovoltaic panels. These heliostats just concentrate the light into the receiver, the tower, that heats up a source of carbon, possibly CO2, possibly some other renewable carbon source, plus water, and it is intended to produce syngas by thermochemical processes, and then syngas is used through the Fischer-Tropsch synthesis to produce kerosene, diesel, and gasoline from renewables, of course. You need both the heliostats and photovoltaic panels because you have two ways to activate these reactions. You have to heat up, and you can achieve it by direct heating through the solar concentrator or with electrical heating using photovoltaic panels. So these are examples of the production of solar fuels through different methods. Of course, hydrogen has been considered in the last years as one of the key solar fuels. And here you find some examples of different methods, the direct electrolysis through different devices. And what is interesting is to see the solar to hydrogen efficiency. It is true that we have a completely free source, but if you have too low solar to fuel efficiency, of course the device, the plant should be bigger in order to achieve a significant productivity. So it is not really an efficiency to say, okay, I'm wasting money for the source. Okay? It is just intended for installation costs that are limited and has this value. And you see that electrolysis is in this moment, let's say, the most efficient way to achieve hydrogen. And these efficiencies are really low if compared with conventional energy conversion systems. You also have some other methods for electrochemical activation, photocatalytic, thermochemical activation, but you see that you are progressively decreasing the efficiency, especially if you are going to directly activate materials in order to produce hydrogen. Is it possible to do the same? So the direct production of solar fuel starting from CO2. In this way, you have two advantages. You are, let's say, reusing CO2, solving the problem of emission and storage. You are overall decreasing the CO2 emissions, and you are producing a renewable fuel. So you can try to mimic all the approaches that are more well established for hydrogen, in order to activate CO2. The use of photovoltaic activation is much less efficient than the case of hydrogen for a lot of reasons. One point is that from the reduction of CO2, you can obtain different products. Formic acid, formaldehyde, methanol, methane, or even achieve the coupling of carbon-carbon to obtain alcohols, olefins, some higher hydrocarbons. The complexity increases this way, but in any case, whenever in a reaction you have multiple products, you have issues with selectivity. And so the efficiency of your system towards the desired fuel decreases, and you have to cope with possible separation issues. You have a lot of problems for the direct electrochemical activation. In practice, only copper-based electrodes are currently sufficiently selective in order to obtain hydrocarbons from CO2. And there are also in this case some prototypes of significant scale, let's say a 40 kilowatt solid oxide electrolyzer developed by ECRES2025, which is a well-known chemical company for the production of synthetic fuels, and in this case it is powered by wind. There are some examples of photoelectrochemical cells, or the simplest ones that couple the semiconductor, which is activated by absorbing solar light, and the catalyst, which drives the reduction and oxidation reactions that are needed, or some more complex devices that try to decouple the two functions, activation one and the catalytic function, in different types of packs. In both these cases, the TRL is still very, very low, and also the efficiencies. Other approaches may try to develop an artificial photosynthesis approach. We are considering systems with very, very low TRL, with efficiencies that are much lower than 1, but also natural photosynthesis is not one of the most efficient processes on our planet. And this kind of approaches try to use the direct photocatalytic activation of states, achieving either oxidation or reduction reactions in order to produce solar fuels. We are interested in all the reduction reactions because you can reduce protons to hydrogen, you can reduce CO2 to different products, or very new, you can reduce nitrogen to ammonia. Also ammonia is gaining a lot of attention as hydrogen energy fuel nowadays. The scale of development is going down from here to here. Now, which are the photocatalysis principles? You have to take a semiconductor, which is characterized by a given band gap. You can tune this band gap by using different materials or by some strategies of doping and so on. Upon the absorption of a photon of sufficiently high energy, higher than the band gap, you can promote an electron from the valence band to the conduction band. And so once you have this charge separation, you can do whichever reaction you want to this energy and the hole, which is a vacancy of electron, so it can uptake an electron from external source. The key point is that these charges should survive, at least for the time needed to drive the reaction, and they have to migrate from the bulk of the material to the surface where they can meet the reactant. And so this is the game that we try to put in place in order to achieve different products by CO2 photoreduction. Of course, we need to couple the other half reaction, which is in principle water oxidation, oxygen, but I'm spoiling you the result. This reaction is very slow, and so it is much better as for the efficiency of the process if you use some sacrificial agent that donates electrons to the valence band to close the circuit. So, first examples of CO2 photoreduction. I don't know how much you will be able to read here. Basically, it is just to say that we have the first records on this reaction around 1995, and all these records up to 2008 were practically based on titania. Titania is the holy grail of photocatalysis. Most reactions at least start the investigation with titania because we know a lot about the photocatalytic mechanisms in titania, but these are the key points. Titania is not active for solar light harvesting, at least in its basic form, because it absorbs only UV light, which is a small fraction of the solar spectrum. Very small productivity is reported. When you come from catalysis, and as in my case, and you approach for catalysis, the first feeling is depression, okay? Because you go down to productivities that are micromoles, millimoles, and something like that. So you have to be very patient. And typically, in order to have a significant speed of the rate of reaction, you need Hall scavengers, that are these electron donors that substitute water, which needs 4 electrons passage in order to achieve the stable product, and so that reaction is too slow. This is one of the key points, because we are trying to make something sustainable, and so if we have to throw away a sacrificial agent, we have to imagine something that should be at least renewable, regenerable, something that is makes a sense in the whole picture. These are some of the preliminary examples. So you see the dates. We are starting from here. Titania with something, titania with different structures, titania with some dopants, and so on. But look here, we have the productivity of nickel, which are few micromoles per gram catalyst per hour. So this is for sure a too small achievement in order to make something with this reaction. Something better, a bit later, we are trying to couple to the evergreen titania something that improves some way the reaction. And here you see, for instance, some metals added to titania. Why metals? Because I told you that we need to form the 2 separated charges, but we also have to let them survive, at least for the time of reaction. And this is not easy, because recombination occurs in a much faster time. We are speaking about picoseconds, whereas nanoseconds is the typical time for reactive events on the surface. So, in order to achieve a better charge separation, one strategy is to put some metals that can be electron sinks. So, you just try to drive the electron away from the semiconductor so that it doesn't recombine with the hole, And you can do it with some metals that have a significant affinity with these electrons, and possibly these metals can also exploit their own catalytic activity, promoting the desired reaction. But still, in this way, look at the numbers, we are improving somehow the productivity, but we are still in the field of micromoles per gram per hour. So, big promises, but also big challenges. What is interesting in CO2 photoreduction is the possibility to achieve interesting products. These in red are the most interesting because they occur faster, because we need a lower passage of electrons. This would be very interesting, but you need a lot of electrons at once, so it is much slower. You may have the competition of water reduction and CO2 reduction. And in general, the challenges are due to the fact that CO2 is a thermodynamically stable state, so you need in general a high potential for reduction. You need to protect the electron and the hole from recombination, and also you are not completely free to select the semiconductor, because you need to couple the potential of the electron and the hole with the redox potentials of these couples that should match in order to drive these reactions. And so there is a problem, an intrinsic problem of solar light harvesting. If we have the need of a high potential for the reduction of our reactant, we cannot use small band gap semiconductors that would in principle be able to exploit efficiently solar light. Then we also have some process limitations. In particular, CO2 has a low solubility in water, so you have to imagine some way to put together water and CO2. You have an intrinsic problem in the scale-up of photoreactors, because you have a third actor, which is the photon, and so you have to predict how this photon distributes inside the reactor, and you also have selectivity issues in case of multiple products. So you have to imagine how to separate these products. So the possible breakthrough in order to pass from micromoles to moles can be achieved by coupling all these improvements. For sure, new materials that should improve itself in the reaction. New photoreactors, and we have some examples of high temperature and high pressure photoreactors. You have to play on the light source, which is for sure in principle solar light. But if you are not sure that every photon absorbed by your semiconductor gives an active reactive step, maybe one of the strategies is I put more photons. And so you can use multipliers, concentrators, and so play on the enhancement factor of different concentrators. All these things, in order to scale up the reactors, need a precise modeling of the radiation and new models to scale up these reactors. And also, photocatalysis comes from photocatalysis for these applications comes from what is well known in conventional photocatalysis for the abatement of pollutants, which is typically done in slurry reactors with your powder of semiconductor, immersed lamp, and so on. All these things cannot be directly exploited in a continuous mode, because you need the separation of So, in a slogan, you have to develop together the material and the reactor and reaction conditions. As for the semiconductor materials, there are different strategies in order to cure the position, let's say, so the energy of valence band, conduction band, band gap, two different strategies. You can improve the efficiency of the formation of the photo charges, suppressing charge recombination through different approaches. One is the placement of some metals, we have already seen, but also coupling two different semiconductors, or removing somewhere else the electron. And different nanoscale morphologies may also be interesting in order to improve the efficiency. Some of the new materials that are much more recent try to use low band gap semiconductors, for instance based on sulfides, or on different oxides. Just have a list. What is interesting is that now at least one of the requirements is achieved. You use solar sources, so at least these are active through direct solar light. But again, you find productivities of ppm, micromoles, with a few examples that run up to moles per gram per hour. Some of these strategies try to combine the semiconductor with some well-conducting materials, such as graphene sheets, that in this case just drive out from the semiconductor the reactor, and then you can place on this graphene sheet some active materials, so active metals, in order to promote here the reduction of reaction, so avoiding the recombination. Or you can couple different semiconductors to different strategies in order to play with some forbidden or allowed transitions between materials in order to drive the electrons on one material and the holes on the other material. So the two reactions are mediated in different places. And you can also use some electrical mediators, such as again graphene sheets, or very new some MXin sheets that are, I don't know if it is the new mood or if they are really effective, but in any case, this composite material. Just another few words on the use of hole scavengers. We said we need something faster than water oxidation. So you can select different hole scavengers. In our experience, this is a very, very active hole scavenger. We use sodium sulfite. And you see that by playing with sodium sulfite, you can play with the selectivity. With this type of hole scavenger at low reaction time, you can achieve formaldehyde, then formic acid, then methanol for very long reaction times. But what is interesting is also that when sulfite is still present into the photoreactor, you continue to produce these carbon-containing solar fuels. When you completely consume, deplete the sulfite, you start the production of hydrogen and CO2. So this gives some hints on the mechanism of reaction that can be different at different pH. Let's see what happens at the neutral pH. You start from CO2. With the first reaction, you go progressively to formic acid, formaldehyde, methanol, possibly, playing with the time of reaction or residence time. But this runs until you have sodium sulfite. So you have to continuously feed sodium sulfite. Otherwise, these compounds start to wet themselves as whole scavengers. So, in the first time of reaction, in the first period of reaction, you produce these compounds, but then, if you don't continue to supply a scavenger, you consume this production, going back to reducing gas CO2. And so you just reverse, you are consuming your product. So this is important from the, let's say, process design point of view. And you have the whole scavenger that is consumed if you continue feeding, you continue producing your product, just to have a number. This is 40 moles per kilogram per hour. It is 4,000 millimoles, so 40 moles per kilogram per hour of catalyst in a pilot scale plant. This whole scavenger, sodium sulfite, is not renewable, so we have considered different types of whole scavengers. For instance, some imines, some alcohols that can be derived from fermentation of biomass. Different productivity I will not detail, but just to have numbers, we are speaking about 3,000 millimoles per kilogram per hour, whereas in the same conditions we have 17 millimoles of 17,000 millimoles of formic acid. So, in any case, sodium sulfite is still the best candidate. Finally, different configurations of photoreactors. You have immersion lamps, difficult to scale up, especially in slide mode. You have examples of optical fibers with immobilized photocatalyst. You have some examples of photoelectrochemical cells, or even some interesting, we are working on this configuration. You can merge a solar concentrator into with a monolithic coated photocatalyst in order to improve the radiance of the system. Our technology is based on a high pressure photoreactor, which is a stainless steel envelope with immersion lamp. The key technology is based on the resistance of the transparent window in order to irradiate the inner tube. In this way, we can improve the pressure for sure, we can arrive up to 20 bars, and at the same time, you can improve the temperature, and this also promotes the reaction. Just for a physical effect, because we are working in aqueous phase, and in this case, you can just improve the solubility of CO2, which jumps up a lot from ambient pressure to 20 bar, and this allows to remain in the liquid phase even by increasing the temperature, keeping a very high amount of dissolved CO2. And irradiance should be modeled, because you have a decay of irradiance which is very fast with the distance from the source. So this is another tip that should be considered. And finally, you have to immobilize your catalysts in order to operate in continuous mode. There are some more or less complex systems, but let's say in order to achieve very first trials, you can just operate coating of quartz or glass tiles with some supports that allow you to just hold your catalyst around the inner ramp that is fitted inside the reactor. And with this configuration, we are able to use more or less the same loading of the catalyst than in slurry phase, but in smooth, high pressure and high temperature, achieving, let's say, some of the most significant productivities that are recorded in the literature for this application. So, to conclude, productivity is still limited for some of the applications of solar fuels production, especially for direct photographic approaches. You have to adopt proper strategies for the scale-up of heterogeneous reactors. You need, for sure, cool scavengers, and one of the let's say, topics of investigation should be to make renewable this point. And at the moment, we don't have a demonstration of these technologies at scale. Just a big thank you to our younger and less younger collaborators, and thank you to our sponsors for the attention.
Thank you, Elena, for the interesting talk. Is there any question? If you have any question, you can just raise your voice there, or you can come here and talk to the microphone.
Maybe I can. Actually, you mentioned about the semiconductor applications for the hydrogen-related energy production. Are there any application for the graphene-based materials with hydrogen reaction or something else?
Yes, there are a lot of examples in which graphene is mainly considered for its electron sink capacities. You can also play quite finely with the decoration of graphene with different semiconductors, so you can also tune the light harvesting capacity of the system, and also playing with the type of metals that you can selectively depose on graphene sheets. Let's say for this kind of applications, for sure, it is a very good exercise in order to understand finally how these materials work, but it is, let's say, difficult to imagine, at least for the photoreactors that are available up to now, a direct exploitation of these materials at scale, because it is also not really proven how these decorated materials can resist over time without leaching, possibly in an aggressive environment. In many applications, you also play with pH, because if you want to drive the hydrogen production, maybe it is better at an acidic pH, whereas for CO2 photoreduction it is much better under basic pH, and some of these materials are not proven for a long-term resistance to this. But for sure, graphene is one of the most studied in the, let's say, after the first examples of titanium-based catalysts.
Any other question? Curiosity? Actually, I have a curiosity. And in order to make an efficient production of these catalysts, do you know some technology based on like 3D printing of devices, or like exploiting a particular topology of materials instead of only
but there are a lot of developments on the assembly of the device. For instance, this supports the green ones were printed, and also some low pressure reactors, photoreactors, have been developed in our group and also in the literature reported from 3D printing. Let's say, probably for the production of the materials, I'm not aware, but for the full assemblies, yes. It is a powerful technology because you can basically obtain every type of shape. So in this case, that you have to very selectively design the shape of the reactor in order to maximize the radiance. This is a fundamental technology for the reactor.
Another question, please. Just wondering, have you investigated the carbon culture system of your studies or your research as a way to reduce carbon?
Well, not directly for this application. In this case, we just use CO2 already captured. In other projects, we are considering the process development of integrated systems for capture and usage of CO2. This is for sure one of the key points, because it is practically impossible to couple this kind of technologies with direct air capture, because you have low efficiency, and so you have to zero efficiency. Yes. But in the case of point sources, it is really fine. For instance, in the Caribbean project, one of listed there, we were considering the case of a ceramic producer in order to capture their CO2. Maybe you can even not pretreat the gas. You can just bubble into the basic solution that you have to feed into the photoreactor, and so this for sure is one of the steps to be integrated. But from point sources, I'm not really aware of possible applications with direct air capture.
Okay, is there another question? So if not, let's thank the speaker again. Okay, and also we have this gift.
Oh, wow. Thank you.
Yes, today we will talk about something very challenging, that is trying to produce hydrogen, that is a very interesting source for renewable energy, but not using fresh water, clean water, distilled water, because the nowadays plants require this kind of very high quality water, but trying to use wastewater. So so covering two problems, producing hydrogen and trying to reduce the pollution in water. So just starting where we come from, the same for Elena, she jumped this part, but we come from Milano, that is the north part of Italy. It's a very beautiful city, and we also try to ask you to come to Milano next year, where we will host the Olympic, the Winter Olympic and Paralympic Games. Now, this is my group, and we are mainly involved in the production of innovative materials, and that's why we are working a lot with Eleni, of course, but also with the University of Perugia. And I mean, this is the new technology my students want that I share with you as were called to join us. At the end, I mean, our focus is to try to work on the Agenda 2030 in order to work on the sustainable development. And so our goal in all our research is to find something in order to work on these specific items. So the idea is to work on the green transitions towards a future society, so circular economy, energy solutions, of course, environmental mediations. As Francesco spoke to you, I also teach LCA, so I mean, just tools to calculate if you are really impacting in a positive way on the environment. So we are producing a new material, just starting from the laboratory scale. We can start immediately check if this is a sustainable material, really sustainable, really green, or not. These are just an overview of our research. We work on air, we work on water, we work on industrial wastewater mainly, and my research and I had a startup on the valorization of our industrial wastes as the topic of today, hydrogen production, and overall, as I mentioned, LCA. So the idea today is to talk about the energy crisis. I will just, a short video for you, just to show you how we are searching the energy day by day, and the energy use per person from 1965 to today, more or less, it's increasing a lot. And parallelly, of course, the fossil fuel consumption, once more, from 1965 to today. And the role of hydrogen seems to be very important because hydrogen stands out as a clean, not abundant because it's not free, of course, but we have many hydrocarbons that are rich of hydrogen, and it's a surely versatile energy carrier. Main features: zero emissions. When we are using hydrogen, we do not emit anything, in case water, actually. And hydrogen can be produced by renewable sources. You know that there are some colors given by hydrogen, coming from black to brown to green, yellow, and so on. Our idea is focusing attention on the water crisis. So the source of our hydrogen is water, but even in that case we have even different colors, depending if it comes from nuclear, once more from the fossil fuels, or in our case, of course, we try to check the idea, of course, we use, as Ilenia mentioned, solar. What is positive or what is also negative? We have zero direct emission. We have, in many cases, hydrogen that comes from, with high purity. It's a very energy-intensive process, and electrolyzers unfortunately requires critical materials. Mainly, they are produced with Italy some years ago, we had a summer season with a lot of problems with water. More than 5 billion people could live in water-stressed regions by 2050. That's why we need to find a solution on this. So clean wastewater, and why not try to produce hydrogen from this source. So the idea in that case is to valorize wastewater for hydrogen generation. We have 6.7 billion cubic meters of wastewater generated every year. This is just the value in Italy, so just to give you an idea worldwide, this is a very, very huge number. And it's impossible to reuse this water without any specific, very expensive treatment. So why don't you try to find this source using this one in one specific stable, particular electrolyzer in order to have hydrogen from this source, in order at the end to have two important points and two important final features: produce hydrogen and have at the end a treated water. I will then show you today two case studies. We are working in this case in collaboration with Polytechnic of Milano, that is producing for us one specific and particular electrode in order to find the possibility to reduce the use of platinum, that is usually the most used electrodes as a cathode or as a anode. We will start with cobalt phosphide. This is our specific product. Now I will show you the use of this as a material, as a cathode. Polytechnic starts with the preparation from a copper substrate. There is the deposition of cobalt phosphide, and we have on top a mixture of cobalt phosphide and red phosphorus. In some cases, we can also treat thermally this material in order to change completely the structure. You can see the difference of the two refractograms from the not annealed and the annealed one at the different treated temperatures. So here are just one short images from the microscope from point of view, just to show you that this material is very homogeneous, and also from the voltammetry characterization to see how this potential is changing, just changing the annealing temperature once more. The final one, the pink, yes, the pink line is the platinum, as usual is as a reference. Apparently, the annealing treatment improves the electrocatalytic performances, as I mentioned, but I mean, seems to be, but then when we try to use this material, we will show a different behavior. First of all, we start with, of course, simulated water. So water in using drugs, in specifically we use pharmaceutical products, so diclofenac, that is worldwide use, and it's a worldwide problem because just think that when we took or when we take one of these anti-inflammatory drugs, more or less 50% of the drug pass through our body, and we expel this. So 50% of the drug of the molecule is not useless for is useless for our body. So go directly into the water, so into the wastewater. It's a very simple experimental setup. We have our cathode now, that is our material. The anode is like I mentioned. We investigated different anodic potential, and parallelly we try to test the diclofenac degradation and, of course, the hydrogen production. Here you can see briefly some recent results, changing the In all cases, that the not annealed one is the best. And just increasing the anodic potential, we will observe a higher diclofenac degradation, reaching higher than 80%. It's not bad. An idea about the mechanism, when we are working at low anodic potential, we have just the direct diclofenac electrooxidation, and so a limited value finally of this degradation. On the contrary, when we are increasing the anodic potential, we are now working also on the water, that is present of course in the mixture, and the water also helps the production of OH radicals, is helping also the indirect degradation of diclofenac, and so we have at the end a higher value of the diclofenac disappearance. From the evolution of hydrogen, we have the same, and once more, our, in this case, annealed electrodes seems to give us very interesting primary results. What happens if we try to increase the concentration of diclofenac in water? Now, in this case, we face a problem because diclofenac solubility in acidic environment is very, very low, so we need to change the medium, and so we try to move into the alkaline environment. This was a sort of challenging because the material, the starting cobalt phosphide, was optimized to work in acidic condition, not in alkaline environment. And in fact, the material from itself it seems to be good also in this new environment, but we observe a lower hydrogen production. In this case, you can see that the platinum is in any case the best electrodes from this particular condition. So we decide now to change, so not using the cobalt phosphide and phosphorus as another, but the cathode. In this case, we change the configuration, and in this case, we observe something completely different. So now, once more, the not annealed seems to be very effective, and we seems to reduce the percentage of diclofenac present in our water, but it is just a disappearance of the pristine molecule. From the COD point of view, I mean the byproducts that are formed into the water, we are reducing the presence of all these kind of molecules only of 16%. So the mineralization is very, very low, that's the point. So we need to do something because, of course, we have to destroy diclofenac, but we want not to have into the water the byproducts. So we want the product just to have CO2 and clean water. So the idea was to couple the electrooxidation with the traditional photocatalysis. Why photocatalysis? This is a very old paper we wrote in Frontiers, just to mention that in many cases photocatalysis has very interesting and potential features, but of course we have also many weaknesses. Sometimes the toxicity of byproducts, for example, like in our case, we have the degradation of diclofenac and total degradation of diclofenac. So in any case, some byproducts could be more toxic than the pristine molecule. The problem is the slow photocatalytic reaction rate, surely, the fast deactivation, and sometimes also the complicated synthesis of the photocatalyst, and the idea that it is not so easy to test them in real conditions. P25, as you know, is the leader of all this, the benchmark of But P25 has several limitations. First of all, P25 works only under UV light, and it is not so safe from the toxicity point of view. That's why we moved a couple of years ago into the lithium oxalides area. With its, we have chlorine and bromide. It's a very, very easy preparation, very fast. The final product is completely not toxic. It's a very cheap preparation, so can be used for many, many reasons. The band gap is very similar to the P25, but we can activate it even under solar light. In this case, I will show you our results with chlorine as dimension 6. And so this is the couple process. So we have wastewater, we have an electrochemical step. After the electrochemical step, we move into the photocatalytic step. And in this case, we have really the contaminated water. Here you can see the final results of the couple process. So once more, in any case, comparing the platinum and the platinum against our material, cobalt phosphide phosphor, not annealed. So we have a first step of electroxidation. Then we move into the other reactor. We are still in the dark, and then we can turn the solar light on, and we now can improve and arrive to an interesting final degradation of the pristine molecule, diclofenac, but also from the COD point of view, so the mineralization or not, we have only 16% in the electro-oxidation reactor, but now, coupling the two, we now reach 60%. That is not enough, okay? It's not yet enough, but it's showing an improvement from the point of view of our research. Second case is just once more how to improve the generation of hydrogen. That is the main topic here also here. We realized that the not annealed sample is the best one, so we try to further investigate this material, trying, as I mentioned, to maximize the generation of hydrogen. And now we move also just not to check only diclofenac, but an additional dye, vitamin B, but also not only the two separate, but the mixture of the two, because once more, if you think to use real wastewater, in a real wastewater you don't have a single pollutant, but you have several, okay? And in many cases you have also bacteria, you have living species and so on. The reality is in any case very, very complicated. So once more, just a few characterizations to check. What is the best potential to be used in order, as I mentioned, to increase the hydrogen production. Here you can see three cathodic potential that was investigated. Minus 0.4, 0.7, and 1. And here you can see the production that we have. I want to stress, because probably before I forgot to show you, in this case the hydrogen generated is in milligram per square centimeter. In the previous slides that I showed you before, the production was microgram per square centimeter. So now we are enhancing a lot the production of hydrogen. Milligram seems to be now something that could be interesting for also for the future. In the slide that you have here on your left, you can see how increasing the cathodic potential you are in any case registering a higher climatic potential, and we are, in any case, improving also the diclofenac abatement and also the dimension of the production. Now we are reaching an abatement of the diclofenac of about 60%. Changing the pollutant, moving into the dye. Once more, we have the same parameters, so milligram per square centimeter, and once more, we are reaching a diclofenac, rhodamine B electroxidation, so degradation, so abatement of more than 60%. Mixing now. Mixing and using a simulated drinking water. So having salts inside. Why simulated? In order to have an everyday constant of the characteristics of our water, so same quantity and same amount and same specific compounds in order to have a reproducibility of our results. So it's interesting to see that the full mark is deionized water. And on the contrary, the empty marks are drinking water, so water with salts. And here you can see how using drinking water and mixing the two, in any case, we can reach quite the full degradation of the two compounds that, as I mentioned, are mixed inside our water. Why this one? Our idea is that in this case, we are also the generation of active chlorine species, diclofenac chlorine inside the molecule. In this is improving a lot the trying to fast also the mechanism of degradation of the molecules. And also from the evolution of hydrogen, even in the case we have improvement. And once more, I want to stress you that we are talking about milligram per square centimeter. So, just a conclusion about my presentation. As you understand, it is preliminary results, but very interesting. First of all, from the material point of view, cobalt phosphide, phosphorus seems to be an interesting alternative to the traditional platinum, or in any case, noble metal electrodes. We can check the use of these materials both at anode or cathodes, depends on our reality. In our conditions under cathodic control, seems to have a very, very interesting hydrogen evolution. In any case, wastewater can be the source of our hydrogen. So the idea to use wastewater as our starting product to obtain hydrogen seems to be possible, okay? And so to couple the idea to have hydrogen and parallel to remove pollutants and so obtain fresh and clean water, not fresh, clean water. In any case, seems also another very important point. If you are working with complex systems, with complex mixture, like in this case, seems that the process is more easy, is easier, and both from the degradation point of view and the production of hydrogen. Work in progress. Once more, changing the environment, moving from the acid to the alkaline one. In any case, sometimes also change what is the presence of the environment inside, and if Polytechnic or you, why not, can provide us with a new kind of innovative material. We are, of course, ready to test anodes, go on with this kind of very interesting research. And so, I mean, this is my group. Once more, I want to thank my sponsors and thank you for your attention.
wastewater and what types of wastewater you refer to. Does this include sweet water, for example?
Yes, sweet, salted, in this previous result, as we mentioned, we are working all with simulated one, okay? We are not working with the real one. We will start with the real one now. We have a collaboration with Monza, with a treatment plant, because one of the most important points, as I mentioned before, is bacteria and the living species in general. So we have no idea how this kind of process will impact with things. So yes, this is very important.
Thank you very much. I have a question about the specific.
Okay.
Now it's a little bit of the technical pollutants.
The two that we choose.
Yes, because you chose
Yeah, we probably have, let's say, an expertise and researches on foods in general. In particular, we are working with Alessandro and here in Perugia with floatable soup works. That is our main research. And in this case, we are trying to reduce the pollutants that are generally present into surface waters. And nowadays in surface water we have pharmaceuticals a lot. The Italian rivers are full of cocaine, Milano the first, and drugs in general a lot. Okay. I cannot test cocaine, that's why I prefer not to be arrested. Dyes, okay. Dyes, we have a lot of, not in Italy, because we have plans to remove this, but if you go into Asia, India, and so on, the main pollutant source is dyes in general. So these are the two main importance. And then if you go, as I mentioned, one of our goals is, for example, agriculture, wastewater. In that case, we will find other kinds of pollutants. In some cases, these ones can be interesting to be recovered before destroyed. But mainly, drugs and dyes are worldwide two main problems. One of the problems of our research, and from the academic point of view, is that we are using, in all cases, distilled water, milky water, and very pure water, and one single pollutant per test. We have to push our research to go towards the real wastewater. It's very, very difficult, really, really difficult. That's why choosing the correct one, but we have to start to mix them. Yeah, this is. So the pollutants are chosen just because, we have that into our laboratory, but the main idea, the main goal is to mix them, because we have to go towards the reality. In any case, this is in any case more complicated. So simulated drinking water, and in order to have salts inside, and mixing pollutants. This is the basic for serious research. This is my conclusion.
Any other question?
Thank you very much. I'm very happy to see this presentation. I have an interest at the research level. However, at the engineering level, I've been working with the oil companies since I was graduated. So is there enough hydrogen there in the well water to overcompensate millions of hydrogen we are right now wasting in the whole planet from the oil industry, it's burning, throwing away. So,
Yeah, and yes, the answer is yes, because as I start the starting point, so the amount of wastewater that we have to treat every year, okay? As I mentioned, I have the value, yes, it is one, the value for but the main part is water, okay? So the problem with the current commercial electrolyzers is that the necessity they require only pure water. They ask you to use tap water, first of all, this is the entrance, and the main part of the plant is to clean this tap water that is already cleaned, okay? Tap water into pure water. There are a lot of parts of the processes for osmosis and so on to have it, to feed the real electrolyzer only with H2O. And this is, let's say, really a dramatic point.
Is there a byproducts other than hydrogen, like where gases perhaps from devices?
Yes, yes. This is the very laboratory scale plant. Okay, the main one should be to separate the anodic and the cathodic parts into one and to recover everything. Yes. We are far from engineerize, say, plants. Okay, but yes, step by step.
Another question? I got a question actually. Do you think also will it be important also to monitor the pollutant in the water, like with sensing devices or like the floating device that we are working with together, no? Like having like a kind of passive sensor in the device in order to monitor the level of pollutant in order to enhance the efficiency of the device.
Speak about concentration or
Yeah, for example, concentration of the pollutant, also the species of the pollutant, so to discriminate which one is can be suitable for that process, for example.
From the electro-oxidation, the answer is no. Especially the idea is that it will be sort of an automatic process, and so it's important to know what is present inside, yes, but not the exact level of contamination. Differently is the second step. So after the electro-oxidation, if you place, for example, a photocatalytic step, yes, in that case it's very important to monitor what is the end. Okay? From the agriculture, for example, wastewater, we reach at the end the final water that can be reused in agriculture, but it is not ready to be used as drinking water. So it depends on the future of the drinking water. Yes.
Thank you very much. So there is another question. Let's thank the speaker.
Thank you.
No problem. No problem.
Actually, we will just start the session. Okay. So I will first announce one of our participants has a working life. So we wanted me to make a change in the program. So I would like to ask ID 107, 108.
then we'll make theoretical, let's say, parameters of performance parameters where the conclusions were drawn off. And then we'll pass to the Albanian power system overview of the system, where we show an illustration of comparison of production and consumption, as well as the net domestic import and export. Then we pass to case study and unlock the results and discussions and conclusions and future work, of course. So the main purposes from which conclusions are drawn in this paper is analyzing the impact of variability of energy production from renewable energy sources. Also will be, as I said, a comparison of energy production and consumption in Albania. And we also have three scenarios or three case studies at Albanian power system with the connection of small and medium hydropower plants and also a large-scale PV plant. All these, let's say, all these scenarios were studied in base of performance parameters of integration of a new large-scale PV plant on the existing power network. So, awareness of climate change and the need to reduce the negative impact of traditional energy and diversifying generating sources has increased interest in integrating a large amount of variable renewable energy sources such as photovoltaic energy. But this increasing penetration normally has its benefit, but also has introduced us to new challenges to power system security due to their dependency on meteorological conditions, which fluctuate across different seasons. So, for example, the output of PV plants, as we know, fluctuates due to factors such as solar irradiance, temperature, and seasonal variations in daylight hours. Literature is rich with the studies of integration of PV plants, but to be honest, it's rare of the impact of PV integration in a daily basis across different seasons that employ multiple scenarios, including peak and low solar radiation days, to determine the variations in grid performance. So, in these slides are shown the performance parameters that has been studied to judge the impact of integration of PV plant with the power system security. In the first column are the parameters, and the second column is its formula. So to make a briefly descriptions, first parameter is line loading. It's nothing else, just a wrapper of current flow of the line with current rate of the line in percentage. Then the second parameter is line loss reduction index, which is the wrapper or is the comparison of line losses with PV and without PV. And third one is line transmission current power improvement index and the cost one voltage decrease criteria. In this slide is, let's say, the picture is showing the comparison between production and consumption, as well as import-export balance of total electricity consumption during the last years, to be precise, 2009 and 2023. The Albanian power system works as a mesh network with a vertical profile, let's say, with the production units are positioned in north of Albania, and the main load is positioned in south of Albania with the capacity of production with about approximately 2,675 megawatt. The primary challenge facing Albanian power system is with its dependency on hydropower, which contributes to 95% of total production, and also as the rapidly increasing demand for electricity. So, let's say the first challenge of Albania fact that we see the production at the year 2023 is high, because 2023 is also called the hydrological year in Albania. So we see that at that year the production surpassed the consumption. In this slide are shown two graphs, let's say, that are a comparison between load and generation, but in a daily basis, in 2 days, in 20 January, let's say, considered as the day with lowest solar radiation, and 20 June, considered as the highest solar radiation. In a daily basis, of course, with contributions of hydro and PV plants installed in Albania. In this slide here is shown the production and present power from southern neighbor country of Albanian power system, like as Greece and Italy. And in these pictures is shown the daily, the total production and transit power in 27 May, considered as a day with, let's say, a lot of import-export energy. So we see that Albanian transmission system is stressed not only by new developments in generation, but also by the increase of generation in neighbor countries, which use our transmission system as a transit corridor for energy transfer to other countries. For example, for Greece, for the transmission between Greece and Italy, it's used our transmission system as a transit corridor. So let's explain our case study. In the picture is shown power output during the winter and the summer day for the Perugia PV plant, which is a PV plant with a capacity of power installed 140 megawatt, or approximately 9% of peak load. And the Albanian power system, as I said, is taken in consideration for analysis. There are 3 case studies that has been analyzed. The base case, which corresponds with maximum load without PV. The second scenario is the day with the highest radiation, in the day 20 June 2024, and the third scenario is the day with lowest radiation. So in this picture are the first performance parameter results, let's say line loading, and these results are taken for the line 220 kilowatts, considered as a critical line in the base case that is more stressed. So here are the results for 3 scenarios, and we see that PV generation significantly reduces line loading, particularly in the morning at 10 a.m. and midday at 12 a.m., where reductions reach up to 37.5% with maximum PV output. The second parameter, line loss reduction index, let's say that by its value we judge about its benefits or its challenges. Let's say with values lower than 1, we can say that the PV integration has improved this parameter, or let's say the power system security. In both cases, we see that the index is lower than 1. But with the second scenario, where at the, let's say, at the highest solar radiation day, the indexes are lower, so this suggests that PV integration reduces line losses, particularly where we see the lowest value during the midday. And the third scenario, let's say the same, the index is higher for PV minimum compared to PV maximum. Let's say the situation is better at the second scenario with PV max. And the voltage decrease criteria where PV generation significantly reduces reactive losses, particularly during the day where reductions reach up to 65% with maximum PV output. Some conclusions of this paper, let's say the results indicate that PV integration reduces line loading where reductions reach up to 37.5% with maximum PV output, leading to improved grid performance and lower transmission losses. So let's say the variability of PV generation, particularly during winter seasons, underscore the need for complementary strategies such as energy storage solution. Let's say this is also our future work to study the power system security by these parameters, but after integration with also different types of renewable energy sources, for example, wind plants or other type of sources, also coupled or combined with energy storage solutions. This was my first paper. Yeah. If anybody, thank you for the attention. If anybody has questions,
Yes, do we have a question? Yes.
You mentioned that the country's current installed capacity stands at approximately 0.67 megawatts. This is actually too little, too low. You mean here megawatt or gigawatt?
no, they installed
For a country that is not
yeah, but I don't know if you know our country, but let's say it's a small one.
very small, yeah, for a country.
Yeah.
Yeah.
So this is the total
In
power
megawatt.
in megawatt. Yeah. Let's say we have three hydropower plants that are main plants.
It's nothing for a
Yeah.
country. Yeah. Thank you.
This is another study about a new approach for optimal phasor measurement units placement, also by our department with my colleagues. Let's say this will be an introduction of phasor measurement units and rules of observability of new, let's say, placement, and our proposed approach for optimal placement. Let's say with the large-scale renewable connected to the power grid, the analysis and evaluation of the safe and sustainable operation of the interconnected system is very important to address the problems and challenges of the future electrical power system. New technologies like wide area measurement system and phasor measurement units will be implemented to maintain the system security to operate closer to its capacity. I'm sure that everybody of us knows phasor measurement units that take measurements at high speeds, typically 30 to 60 measurements per second, compared to a measurement every 4 to 10 seconds using conversion technologies. So why good news? For three reasons. For state estimation, stability and control, and of course protection and monitoring. Let's say in these slides are shown some rules of observability for PMU placement. For example, a directly observable node is a node which a PMU is installed. A computational node is observable by other PMUs but doesn't have one installed itself. A node is said to be unobservable if it cannot be calculated due to one or more unknown parameters. Complete observability refers to a system which all nodes are either directly observed or calculated. Incomplete observability refers to a system which some nodes cannot be observed. So here are, let's say, the words that you say in a mathematical background. For For example, rule 1, all neighbor nodes to a node carrying a PNU are themselves observable. And second rule, if a node without an interconnection is observable and all nodes connected to it except one are observable, then that unobservable node also becomes observable. This is a comparison between SCADA and PNU. Let's say we make the difference between two technologies. For example, of the type measure, let's say SCADA uses analog signal, meanwhile phase measurement units use digital, and the resolution is, let's say, higher with the PNU. Let's focus on the proposed approach for PNU optimal placement. There has been analyzed two cases, or has been taken in consideration. The first case study, or the first scenario, without considering the bus characteristics factor, and the second scenario, taking into account the bus characteristic factor. So let's say, firstly, we define the incidence matrix. Then we calculate, let's say, about the criteria of voltage stability with the sensitivity coefficients. Also, then we define the best characteristics with factor T and the modified incident matrix. Let's say we will see later. Identify buses with the maximum vertices value, and then if there are unobserved buses, let's say we should return to this step. Lastly, are made a list of PNU placement in the case study of data. For analysis is taken the 14 bus system of IEE, which is used to illustrate the proposed approach. Let's say with the first scenario, without the consideration of bus characteristics, are taken in the first matrix, which is the incidence matrix, are taken the nodes. Let's say, like we said, with the rules set here, interconnection points, which are dynamically the most important buses in the system with factor P greater than 1, the most sensitive buses of judged by voltage stability criteria, and generating buses, also transformer buses. After, let's say, after mathematical judgment made here, we in the last matrix we determined the nodes where PNU or phasor measurement units will be installed. This is the second criteria, where firstly, let's say, are taken the UQ sensitivities or coefficients of sensitivity based in voltage stability criteria, where are made the same logic, but the results are different. We'll explain later why. So by this simulation, let's say, or I don't know, by this study, the results indicate that following the logic of the second case, we observe that the number of PNUs is lower than 30% of the number of buses, which is a criteria, or let's say, which is a rule. In Albania, let's say our case study, there are 6 phasor measurement units installed at power system. Let's say is a low number for I don't know, for international power system, but for our local power system is great. There are 6 substations where installed these phasor PNUs, and these have been installed as standalone physical units with 4 integrated modules with voltage and current transformers, which monitor a total of 10 lines. This this is also a geographic distribution of PMUs in Albania. Six that also connect with interconnection lines, for example, with Montenegro and Greece and Kosovo. Let's say with the lines as written here. And some conclusion, let's say this paper presents a newly proposed approach to solve the optimal PMU placement based on a multiple objectives such as the base bus characteristics factor and the bus sensitivity to determine through voltage stability analysis. As we saw, the IEE 14 bus system is taken into consideration for analysis and to illustrate our approach. And the different numbers of PMU sets are obtained by comparing the proposed method with maximum vertices of incidence matrix. We can notice with the proposed approach, the second one, the maximum number of PMUs used is 21.4% less than the 30% of the total number of system buses, which is the limit. Between the first case where no bus characteristics factors is taken under consideration and the second case where the bus characteristics factor is considered for PMU placement, the PMU solution results to be differently. We conclude that the location of buses in the power system is a key factor in determining the best strategic location for PMU placement and must be taken in account. Thank you for your attention.
Okay. Only one question if you have. What about the fault? I mean, if a fault occurs in the system, we have
we have, let's say, the protection with relay and other distribution panels in the fault happen. Let's say also the PMU is not, let's say, studied in our paper, but the PMU installed at this place, of course, has its protection panel, let's say.
Thank you. So you can have your case. Thank you very much.
Thank you very much.
So now we can continue for the first. Yeah, Hamdi Ezit is here. Hamdi Ezit. So we can. Sorry, the session chair Fernandez, Jesus Andrews is here. So maybe you can come here and you can do that. So so we can start with 3, ID 3, so that we have a flag. So 10 minutes for each and 2 minutes for the supposed to be 4 in this session, where we can now download the slides so we can move easily.
Can you call the names, please?
Yes, please. The people in the name as Ezit, my apologies if my pronunciation is not okay. Ezit Henry, Antonio Ariel, and Alberto Monterosso. So now is the time to download so we can progress nicely. Slowly, because we have very long before we how are you? Everyone is safe? Okay. I will try to aim for coffee time. All right, so. Anyone would like to come and go because I'm conscious of the diversity of the group, and for some people the cracking may be a little bit a source of discomfort. Anyone would like to go in and out?
We can start at 11:30, yeah?
2 minutes? No? We are done now. Just done the presentation. I guess in case of any emergency, the exit is here against the evaluation plan. That's the safety, right? We are just uploading the presentation, so we will start once more.
Good morning, everyone. My name is Alex Mejra. I'm from University of Lisbon. Today I represent my statement of myself and engineer Jonas entitled Solar, Wind and Energy in Carbon Dioxide Refrigeration System for Sustainable Fish Cold Storage Solution. This proposal project is to turf out Santiago small seeds in Santiago Island in Cape Verde, coast of Africa. The study's objective is to evaluate the energy efficiency of an integrated cold storage system, determine the financial viability of 4 different cold storage strategies, analyze the environmental impact of the 4 strategy, analyze the return on investment among the 4 strategies, demonstrate the contribution of renewable energy source to long-term energy supply. The Terraform seed is a small seed in Cape Verde. The seeds depend a lot of fishing and fishermen. We can see the layout, the proposed layout for the facility of refrigeration with buffer, freezer chamber, refrigeration chamber, and in left we can see the bay of the seeds. This seed is it's a perfect seed in terms of renewable energy with a lot of sun hours, with high wind velocity and high merging current. The climatic condition of our Earth as follows. Dry bulb temperature of the design is 35 degrees Celsius. Relative humidity range is between 60% and 85%. Average wind speed is 26 km/h, and average speed of marine currents is 6 km/h. We can see the sense and direction of the wind and the marine currents. And right, you can see observe the weather of the sea. The product preservation condition as follows. The product is fish. We have the refrigerated storage temperature between 0 degrees Celsius to 2 degrees Celsius. Frozen storage temperature between -30 degrees Celsius to -20 degrees Celsius. Relative humidity between 90% to 95% for frozen products and 95% for refrigerated products. We can see at the table the thermal loads, different thermal loads for freezer chamber, refrigerator chamber, and buffer. We have thermal loads from production, thermal loads from products, internal thermal loads from infiltration, and we have the coolant power of the valve chamber. We use the photovoltaic panel solar, wind turbine and thermal energy to transform the renewable energy proposal. In order to understand the adventure of our proposal project, we compare with other three solutions. In the first strategy, we consider two centers with one 3-4A refrigerant, one for frozen fish, one for refrigerated fish, and electrical power supplied by public grid. In strategy 2, we consider one center, a carbon dioxide transcritical booster system for refrigeration system, and electrical power supplied by public grid, the electrical grid. In strategy 3, this strategy is our proposal project. We consider one center with carbon dioxide transcritical booster, electrical power supplied by autonomous electrical power generation system with tidal, wind, and solar panel. In strategy 4, we consider one center with carbon dioxide critical booster system, electrical power supplied by autonomous electrical power generation system, wind and solar panel, and condensation process through heat exchange with fuel. The results in first study, we study the coefficient of performance of this whole strategy, and we conclude that the strategy 4 is the highest score with 30.02. In second study, we study cost and payback, and we conclude that high initial investment in 3 and 4 demonstrate better financial stability. Although strategy 4 has a 5-year investment payback period, it represents the same initial investment and low initial investment than strategy 3. In carbon dioxide emission study, we conclude that the strategy 4 was identified as the best option in terms of overall CO2 emission, emitting approximately 16,000 kilos equivalent of carbon dioxide. The adoption of an autonomous electricity generation system resulted in a 9% reduction in CO2 emission compared to electricity source from the public electrical grid. Conclusion. Strategy for supercritical booster refrigeration system with CO2 with CO condensation emerged as the most favorable option. The result is with solution 1 discouraged due to the use of one 3-4A with high global warming potential investment payback period and high CO2 emission, approximately 30,000 kilo CO2 equivalent. Financial analysis confirmed that the ability of such grid despite high initial investment. Present study highlight the importance of integrated renewable energy into the refrigeration system, contributing to achieving the environmental goals set forth in the Kyoto and Paris Protocol.
Thank you. Very insightful. Any questions?
Yes, what about the life cost assessment? You mentioned payback period. You didn't tell us anything about the life cost assessment. This parameter is very important in assessing renewable energy. I mean, how much we pay per kilowatt hour. This is called the Device Process System. LCO. So I think it's important to consider this parameter when you study if you didn't published it yet.
In terms of costing and payback, we consider the initial investment.
Yeah, which is 3 years, I think, yeah? It's for the best scenario or the best strategy.
Yes, because possibly it's the best scenario. With the investment in renewable energy, we don't need to pay the electricity from the grid.
Yeah, it's free. It's free.
Yeah, it's free. We have high investment, but we can get the
For example, in your country, how much you pay for the power company per kilowatt hour?
16 euros per kilowatt hour. 16 euros, yeah.
That's too much. Yeah. It's cents, you mean? Cents?
Cents.
Yeah. Cents, yeah. Okay, so it's helpful to compare what you pay to the company power and what you pay now according to your strategies you suggest to recommend. Yeah. But this is called the device process system. Okay.
I think the recommendation is an excellent recommendation to
Another question.
Thank you very much for your presentation. My question is, why is the cause of refrigeration R1348? Also, I think your COP is higher. Your COP, your question of government, the validation of it. The question of yes, for me it is so high.
any parts of one?
Why?
Reports 1 or reports 4?
Four. Look at the value. For me, it is so high.
It's so high because it's a supercritical system, and the condensation is it's made with sea water. That we have a low temperature in sea water, and with the supercritical system, we have a lot of energy to condensation with sea water. That is the reason.
And the cost of refrigeration R1348 secured.
It's just one solution, but the our proposal project it equals to it.
Okay.
If you are happy with the approach, we still have 1 minute for the last question. If you like to go over time, or just tell me, but I think time. It's time for the last question. Questions? No. Thank you very much. Very, very by bioengineering research group. We are establishing Canterbury in England, is basically a new provision in engineering. We are new in engineering in the southeast of England. And when I arrived there was just rubble, there was nothing. We created engineering there. We are new, and yes, but we are not in the business, but we are in the University of Manchester, the University of Nottingham, there as an associate professor, as well in an MIT, as well as the organization. I usually investigate value-added products for biomass, biorefineries, something I directed in Manchester for quite a while, and ionic digestion. We also do some fancy stuff on random mutations and directed evolution, something we borrow from Caltech. And then we try to investigate advanced biofuels, and as well we do LCA studies in whatever we do, a lot of stuff in bioprocessing for vertical farming, trying to introduce robotics, bioprocessing, and future farming. It means agriculture, but without the land. My experience started in 1994. I was from the oil industry. You know, oil industry produce a series of products from gases to waxes and a lot. Oil is still in 95% of whatever we see here come from somehow from oil, and it's still a very profitable industry. It generates trillions of dollars, and also an industry that requires money from governments. For instance, a report is telling us that 82 countries are still subsidizing the oil industry, contrary to what people believe. And in that society, we have many trending topics. People are worrying right now about climate change. I can't remember the name of a teenager that is also, you know, on Facebook, and people are talking about people not clean water, more food. People are thinking renewables. Right now, here in this forum, the first talks were related to renewable energy, how to use waste, and so on. In my domain, we are worried because we're going to say goodbye to fossils. We are still dependent, and we are trying to find feedstocks that replace oil for biorefineries. We need more and more feedstocks. We have different agendas in the United Nations, in the International Energy Association, Mission Innovation. In Europe, we have the EU Green Deal to reduce by 55% the greenhouse emissions by 2050, or the Renewable Energy Directive as well, to increase the share of renewables by 2050, little more and so on. But we just don't find the solution. Even in the UK, we are talking about right now budgets of carbon, like having money. You know, as the time passes, we are right now in the 5th budget to decarbonize the UK, and we have trying, you know, we are trying, and as we can see here historically, because historically the humans have tried to find different feedstock. First of all, we proposed using food like wheat, corn, and so on, but it created a scandal. The Italians were complaining because they didn't have pasta, or the Mexicans didn't have tortilla, because the corn products could produce biofuel, and we said, yeah, we need to find another solution. Then we proposed lignocellulosics, and the lignocellulosics are very tough and recalcitrant and different, and at the end the LCAs didn't make sense, and then we said, let's destroy the Amazon forest, and things didn't go okay, and then we said, let's try to use microbes, microalgae and so on, large investments on microalgae, and then we discovered that they are prone to disease, contamination by viruses and so on, and when the wind comes, they pollute areas with very nasty aerosols, and then we said, let's go for another generation, let's go for the engineer. I call them engineer because they could be genetically modified, but now we have epigenomics that has nothing to do with genes, and we discovered that manipulating those characters at the level of some molecules that are there in the epigenome of microorganisms, we can even modify the outcomes, as Lamar used to say many years ago. And we believe that there is a little room there down, and that's what I want to propose here today in this conference in Perugia. The problem is that no matter what we do, we have a sustainable biomass. We also need to have a sustainable conversion. What we are proposing is to use, for instance, added plants, like the ones you see here. And by the way, at the beginning I thought there was not too much there to do, and not many countries were producing that biomass. Do you know who is the second largest producer in the world of that biomass right now, today? Do you know?
That?
Italy. It's Italy. It's not Mexico, by the way. They are tough plants, they require less energy, less signification than algae. They grow even in my room, in Britain, in plastic, over this desk, if you want to water, they grow there. They are receiving, they capture carbon dioxide, not only by day, but also at night. In fact, they are so powerful and inventive that I told that many years ago, they produced the greatest plant invasion in humankind history. I didn't like it, I didn't know that much about it, and as soon as I discovered, I said, oh, wow, they are so powerful, more powerful and more produced than microalgae itself and sugar cane. But again, the problem is how to make sustainable this biomass when farming it without destroying the forest, and how to improve the conversion. And we have to improve the system of thinking, how to make it cheap, easier, safer, and environmentally friendly. And that is tremendously difficult. And more difficult to bring together agriculture and oil refinery. How to produce those plants, but also to process. I'm going to present you very quickly. And then what we did is basically integrated the yin and the yang, farming and the plant. We brought together agriculture and refinery together, analyzed all the different processes in 4 cases, by the way. And when the COVID came, it was a disaster. But the 4 I am presenting here is just the ones that more or less build up the story. This is a simplified version, even though here, where we all know, especially in the biorefinery. In the first case, I'm using the classic biorefinery. That process we discovered that was not cleaner, and it was not self-sufficient in energy. And now that's no matter what, many refineries in the planet, they have to close or shut. Unfortunately. Then we came with another proposal. We use organic biofertilizers because people, they say, if you use organic, things are good, not necessarily. We discovered that it was a little bit cleaner, but it was not energy efficient. So what people believe is not necessarily true. Then when we implemented ionic liquids, because the chemists, they said, ionic liquids is the solution. Oh yes, let's see if that is true. We discovered that it wasn't, by the way. The system was still dirty, and then it was not energy efficient. And then we discovered a system that it was cleaner and energy efficient. We applied the LCA system. I'm not going to give a lecture in the LCA here. We can chat about that during the coffee time. We integrated different type of inventories, and then we run the first number. We discovered that the first case in light green is essentially okay. Then when we deployed the biofertilizer or composting or manure, it was a little bit better, cleaner, but not energy efficient. And when we applied the ionic liquids, it was a disaster, right? The chemical solution, it doesn't seem to be okay, and there are wrinkles around there. And the fourth, which is in orange, is the champion. We produced something that was cleaner and energy efficient. And in this graphic, we are showing which processes in the refinery, in the process, transportation, and farming are the major contributors to the development, the ones that are not environmentally friendly. We discovered that in terms of energy, case for the wind can give us the energy even more than the energy that is invested in the whole cycle. It means that the system could be self-sustainable to produce energy. And we could see here when compared with other technologies, including smoking sugar, cane gas, and some groups are doing that in the Netherlands or in France, compared with wind as they are doing in the United States. So we can compare that, and our system, which is here, the last one, using these ag plants, is highly competitive for the energy return on investment. So people will say, but it's not that much. Yes, but it's not that much. So probably in the future, it will be competitive, as we can see here with the cumulative energy demand. So producing the same amount of the biofuel correlates with a tiny amount of cumulative energy compared with the traditional and classical refinement. So in conclusion, we found a system that is energy efficient at the same time, using an added plant, which is the model to say that added plants can help. Because at the moment, I would like to say that the plants that we are using for the green revolution are plants that are being, half of the planet right now is on light, and the half of the planet is in the dark. So we haven't been thinking in the dark side of it. At least these plants, they can be working during the night, while the others can work during the day. So in conclusion, we have a system that can give us the energy that we need. We can produce a liquid biofuel that is sustainable. So that can help us with a positive circular economy, the things that regarding the development goals, climate risk, and help us perhaps to save this planet, and perhaps we can propose a fifth generation of feedstocks that can help us with the future. Having this results, I can tell you it was not an easy task. We have doors closed in every journal that we sent it. Of course, right now the narrative is in the algae, there's still lignocellulosics and so on. And when you arrive with something new, the doors are always very, very close. And we tried to climb, and we were very happy that the greatest journal in energy at the end, after 3 years of trying, it was the one opening the doors for this research. Thank you very much. If you may have any questions, I'm very happy to answer you.
There are many different types of air plants.
Yes.
Maybe, for instance, in the Asian side, I can say that there's 50 different
Yes,
types. And are there studies on which type of air plants
yes, yes. In fact, in 2018, when in this project, by the way, something I didn't do alone. Happily, I was invited by colleagues in the United States and one from Mexico, me from Britain. They were trying to convince me. I didn't have any hope so far. And then, yes, I started investigating and checking. There are many plants. And I said, look, we need to find a model. As the biologists, they have some rats, or perhaps the zebrafish. We found this plant, and then finding this plant because we compared it with more than 70 type species from the Mediterranean area, from the East France, or from Turkey. Yes, and then also there is one, but then this is just the model.
Does this ongoing study?
Yes. I mean, this is the proposal. We got the model, and then we can extrapolate right now. Of course, it's the model that is more fleshy, it has more carbohydrates, it can give us, those impactful results that we want to see, but there are things. Any other question?
Thank you for the presentation. I'm wondering which is the type of substrate that you are exploiting for fermentation in this kind of plants. Cellulosic, I don't know, because I completely do not know anything about these plants.
Right. These plants, they look more or less like a sandwich. The very flat is the lignocellulosic material. It's a very tiny or thin skin, like paper. And between the two layers, we have kind of fleshy stuff that look more or less like the jelly that we use for cleaning the house. So that jelly part is rich in carbohydrates. And this is the part that we separate, and then we send to enzymatic degradation, and then to fermentation to produce ethanol. Yeah, so that's the
You have to select
when we have no way forward. So what we do is we grow some microbes, very popular microbes, not genetically modified, and we get those enzymes to chop down very quickly, you know, this fermentation, we do it in our kitchen with yogurt and so on, in a very easy way. Yes.
I think the good thing that you consider life also system from the beginning to the end of the cycle. So can we say you use the concept of from cradle to cradle?
Yes. Yeah. Yes. I'm going to engineer, by the way. I do biostuff, but I am a chemical engineer. We try to introduce all these methods. Systems engineering. Thank you very much.
We have other presentations. Yes. The presentation of Alberto Monterosso.
Good morning, ladies and gentlemen. My name is Alberto Monterosso, Research and Development Engineer at the National Institute for Aerospace Technology in Spain. In the presentation, we're going to talk about energy conversion from electricity to green hydrogen, that is chemical energy. Specifically, this presentation is entitled Mathematical Knowledge and Experimental Simulation of an Ion Electrolysis System. The topics of this presentation are stated below. First, an introduction to the main electrolyzer technologies and the main objectives of this work are going to be presented, followed by the methodology and model description. At the midpoint of this presentation, we are going to talk about the experimental validation of the aforementioned model, as well as the results, and closing with a brief conclusion. So, starting off, among the electrolyzer technologies that are currently being implanted, alkaline is the most extended for green hydrogen production. It is the first to be invented, and its good rankings in efficiency and reliability have influenced its wide implementation. However, with the increasing deployment of renewable energies, more flexible solutions are beginning to be needed. In this regard, on the one hand, we've got PEM, which is proton exchange membrane, excels in dynamic response and compatibility with fluctuating energies. On the other hand, ion exchange membrane, with a 6 to 7 kilogram score, provides a cost-effective solution between alkaline and PEM, while maintaining similar properties to the latter. The drawback is that ion research is very limited, as it is the youngest of the three technologies presented, and the main focus is on the materials at a chemical level. The objective of this work is to develop a comprehensive ion electrolyzer model that includes and accounts for the electrochemical properties of the stack. As a step further, this model has been validated up to 100 hours of experimental data. The methodology is based on classical nonlinear parametric approach And in the left figure, we can see the general block diagram of the model with two inputs, mainly the stack current, which is the set point, and what we call additional physical constants, which have been tuned for the specific use of ion electrolysis. The output of the model is able to predict the stack voltage, the hydrogen flow, and the stack efficiency. This model has been implemented in the MATLAB Simulink software. Digging into the insights of the model, we have derived the equation from the first electrochemical principles. In a generalized electrolyzer, the stack voltage is the sum contribution of the reversible potential, the activation potential, ionic, and ohmic potential. We can see clearly the nonlinear nature of the model in these equations, and the influence of temperature in everything but the ionic and ohmic stage. At the right side, we can see the hydrogen flow formula we have employed for the results, as well as the efficiency. It is worth noting that the efficiency accounts for the low heating value of the hydrogen molecule. Moving on to the experimental validation, three tests have been conducted. First, a polarization proof to analyze the steady state, which consists of stepwise increments in current with an amplitude of 0.5 amps and a rest time of 3 minutes for the full operational range of the electrolyzer. Secondly, long-term stationary test in order to obtain very precise and accurate data at a steady state. In this case, ion operates for 5 hours at several constant power levels, ranging from 60% to 100% of the maximum rated power. And finally, the most challenging test we have conducted are two photovoltaic energy profiles to measure the dynamic response, which is a thing it is not usually taught in this scientific field, the dynamic response, with a winter cloudy profile and a non-demanding high transient profile. This is a photo from our laboratory and the electrolyzer we have been using, which is a 2.4 kilowatt unit from an Aptel brand, model EL4.1, with a nominal H2 production to be highlighted of 8.3 normal liters per minute, a maximum pressure of 35 bar, and a water consumption of 0.4 liters per hour. Well, these are the results of the model. At the left, we can see that the blue curve is the experimental true stack voltage measured in our experiment, and the red line represents the simulated voltage from the model. We can see that the overall envelope of the operational range has been covered, while the differences we see in the blue line are mainly caused by temperature perturbations of the model. We can see that a peak efficiency of 65% is achieved at the lower power levels. The second result is the stationary test, and we can see that the set point is accurately reached with low offset error, as well as a stack degradation tracking in millivolts per hour for limited to the first 100 hours of operation of the machine. Finally, the third test is the most challenging. It is a dynamic test with several levels of difficulty. On the left side, we have a moderate, and on the right side, a highly demanding test. And we can see that the dynamic performance of these new electrolyzers, in particular, is very good. In all the tests we have performed in our laboratory, we transient response improvement, stack derivation modeling, and the availability of larger data sets. These are the references included in this presentation, followed by the acknowledgements to the project H2, funded by the European Union Next Generation, the OER H2 project, funded by the Andalusian government, and IRE project, funded by the. With all things said, I am open to answer your questions. Thank you.
We have 3 minutes for questions. First question, please. Any question?
Maybe I can ask a question. You have shown 2 plots to us, one experimental and one theory, and there are some differences between theory and experiment. What can be the reason for that? Probably the reviewers will ask this question to your paper when you submit it to a journal. Yeah?
May you tell me the...
Yeah, this one.
This one first.
Yeah. I mean, why is this difference come from?
Yeah, we can see that the accuracy of the model is actually very good at the x-axis in terms of time response. Mainly in the y-axis, in the amplitude part, there are more errors. Those are caused by observations, very stiff design parameters of the model. It is very constrained in that sense. And also the degradation effect of the stack, which increases gradually the voltage. So I see mainly those 3 reasons.
So you should also mention about this limitations in the paper.
Yeah, that's a good thing for
Did you measure this gap? Like person, for example, did you measure it? Because this is a kind of validation, model validation. So I think you need to provide some measurements in person to reflect the error.
The measures have been limited to the mean average error. For sure, there is room for more analysis. It's quite interesting.
Just for the last suggestion, for validation, for me, you must calculate the difference of the error between the numerical and the experimental state.
That's actually something I'm going to write down. It is actually really interesting. Thank you for your questions.
Thank you. Thank you. Excellent. Thank you.
Sospende da tipo pochi minuti. È comparso un messaggio fra 5 minuti e sospende. Devi premere qualcosa sul telecomando. Sì.
He wants to use
okay.
That's what we did.
Cambia solo il volume, magari.
Thank you for making the discussion.
I really enjoyed it. It was like a course.
I really enjoyed it. I really enjoyed it. Very well.
Sì.
you everybody. So we have now the last presentation for the session.
Just left upper part. Questo is.
Vai, vai, più.
Directly from the USB.
This work is done also at the same time you can start by presentation plan, by introduction, then I will present some preparation of my energy harvesting slides. Then I will do some tests and video preparation of my product. So after that, I will study the impact of load resistance on the output voltage curve and power. I will make the studies, then conclude. I will start by some definition of this. For the effect is known as the when we apply a force to this electric material, we obtain a polarization or electric effect. Also, we have the inverse electric effect when we apply a voltage to the electric material and we obtain a deformation. These two figures here present two types of direct effect. The longitudinal effect or when we apply the force longitudinal to our material, we obtain a polarization perpendicular to the material. For the DC mode, when we apply a force perpendicular to the horizontal of the material, we obtain a polarization in the same direction of the material called the DC mode. Okay. This figure presents the molecular structure of our periodic.
We know PVDF at its inner structure is alpha phase, is inner, not is electric. To transform our material from alpha phase to beta phase, we need either stretching or pulling our material. Pulling is to apply electric field to our material, and stretching. So, in this slide, I present some application technology for PVDF material. We know there is many applications of PVDF. We can use the nanogenerating, geometrical application, super capacitor, and flow sensor, and many applications, muscle, artificial muscle, and geometrical application, and many applications. Okay. I will start by how I prepare my device. I will see that I treat all this preparation is done at this material. Okay. We buy first of all, we buy our PVDF polymer from United States. The PVDF has the characteristic of differently around 30 picocoulomb per newton and a thickness of 410 micrometer. Also, we prepare our ECRES2025. The material the PVDF cannot be introduced in the human body because it's not biocompatible. So we need some biocompatible material like PDMS or ECRES2025. For my case, I use the ECRES2025. For ECRES2025, I use a technique called Dr. Blade. You can see the Dr. Blade is the machine. Okay, this is the ECRES2025 with two flakes A and B. We take 5 grams of ECRES2025 from flake A and 5 grams of ECRES2025 from B. Then we mix very well and the solution becomes very homogeneous. After that, we burst our ECRES2025 in the glass plate and we fix with the Dr. Blade the thickness of our ECRES2025 and after that we obtain our film. After the decoration of our film and using a resin, we prepare two prototypes. One prototype was with one PVDF and two ECRES2025 and the other one with two active PVDF connected in parallel with the electrode and 3 ECRES2025. Okay, this is the schematic of our energy harvesting device with one PVDF and two PVDF. You can see that we use the epoxy resin to connect it to the ECRES2025 and the PVDF. Okay, now we do some banding test to obtain the output voltage. Okay, the banding test is composed of an oscilloscope, a vibrator, a low frequency generator, and one CFOR. We fix our PVDF from one side, and the other side is free. After that, we apply different frequency, 1, 2, 3 hertz, and we obtain our output voltage with the oscilloscope. You can see that the output voltage is around some millivolt, and it increases with the frequency. In this figure, I plot the maximum output voltage with one PVDF line and two PVDF line. You can see that connecting two PVDF line increase the maximum output voltage. Okay. In this slide, I use an LCD method to measure the capacitance and the impedance of our energy harvesting device. We can see that for piezoelectric material, the problem of piezoelectric harvesting has a higher impedance. So our idea that if we connect two PVDF lines in parallel, we can increase the capacitance of the material and we decrease the impedance. You can see it clearly in the back figure and other figure. Okay. The problem of PVDF has high internal load resistance. Its load resistance is around 940 mega ohm at 1 hertz. The most of the oscilloscope we use has a load resistance of just 1 mega ohm. So really we cannot see the real output voltage. We see around some millivolt. You can see at low resistance. You cannot see the real output voltage. The idea is that if we increase the output voltage, we cannot see the real output voltage, the current and the power. You can see that we can do that at resonance, which is air and resistance. We can reach for our 1 kVA flyer output voltage of 2.2 volt. For this I compare the output voltage for 1 kVA flyer and 2 kVA flyer. We can see that for the 2 kVA flyer I can rush output voltage of 3.3 volt. We can see that this output voltage can be used for many applications like pacemaker and other geometrical applications. Okay, some conclusion. The conclusion is that we prepare our energy harvesting device. We also prepare another experimental setup using LCR method to use the electric characteristic of our energy harvesting device. We can see that using the energy harvesting device with multiple PVDA increase the maximum output voltage, increase the capacitance and decrease the impedance. Also, you can see that increasing the load resistance at R equal R internal resistance can increase the output voltage of the multiplier and can be used in many biomedical applications like pacemaker, heartbeat monitoring, and many other applications. Thank you for your attention. By the way, this work is funded by Marie Curie application, thanks to the European Commission. And our project is named New Energy Harvesting Technology for promoting battery life of unpluggable electronic devices. Thank you.
I have a quick question. Thank you for your presentation. What about the capacitance of your devices? Do you have typically what is the capacitance?
Definition of
No, the capacitance of your devices. You have.
One line or multi-line?
I don't know.
Because first time I do one PVDA is 2 ecoflex.
Yeah.
I'm using the capacitance. You can see this graph. This is the capacitor of red one.
Okay.
After that, we do 2 PVDA and connect it in parallel.
Okay, so it's 10 to the minus 10. So you are below nanofarad.
Yeah.
Okay. So have you tried to change a bit the geometry, having
It's another application. Because some people use helicoidal geometry, but it's a real application. This just is a product.
Okay.
It's complex to real application with helicoid structure or ligament structure or other structure. But it's just a product.
Okay. So because I think this is why you have such high load in when you are measuring the performances and the power output. Okay. Thank you.
Second question. The last one. Thank you very much for your presentation. So here's you wish you can go to your presentation and then we the certificate here. This is for you. Thank you very much. Maybe 15 minutes
se vuoi lasciare
tu lo lasci basta
no, non lo so, lo ruberà se vuoi lasciare roba qui dici
Ben ne yapacağım şimdi? Ben bunu kapatayım mı? Elimde kaldı çünkü. Ne yapacağım şimdi? kapatıyorum.
Bataryası nasıl? Batarya
Kapatıyorum. 28 bunu şarj etmemiz lazım.
Tamam kapat. Hı hı.